Hey everyone, welcome you all to the YouTube channel of DCC NIT. Myself, Mayur from third year Computer Science and Engineering, NIT Agartala, and today I'm going to discuss the problem Koxia number theory that came in good by 2022. That is the last contest of this year. So the problem statement states that we are given an array of n positive integers and we are asked to determine whether there exists any positive integer x that's greater than 0 such that the pairwise GCD when you add x to them, that is ai plus x and aj plus x, that is equal to 1 for all pairwise integers. So if we take a look at the example, you can see that when the input is 5, 7, 10, so we can add 4 to all of them. So it is like the number becomes 9, 11, and 14, and you can see that the pairwise GCD is 1. But for 3, 3, and 4, we can see that like whatever we add to them, the GCD of 3 plus x and 3 plus x, that is always 3 plus x. Like from this we can conclude that like if there is any number that is repeating in our array, so whatever we add to them, the GCD can never be 1. The GCD will always be that number. So the answer is always be no. So from this we get our first conclusion, which is that like if we find a repeating number, the answer will be no. Now we have to check for other cases. So let's start with small example first. Like this is basically like if you try with examples, then only you can observe like how to solve this. So we'll start with a small example. Let's take 3, 4, 5, and 6. If I add 1 to them, the number becomes 4, 5, 6, 7. Now here you can see that 4 and 6, this is GCD as 2. So the answer will be no. Now if I add 2 to them, so the numbers become 5, 6, 7, and 8. Here you can see that 7 and 8 they have GCD as 2. So the sorry, not 7 and 8, it is 6 and 8. So the GCD will be 2 and hence no. Now, if I add 3 to them, the numbers again become 6, 7, 8, 9. So again we get 6 and 8. So this again no. So you can say that whenever we add any odd number to those, so the original odd numbers become even, and so the answer becomes no because this is 2, or like it will be at least 2 or anything more than that. Now, if we, on the other hand, if we add any even number to the whole num to all the numbers, so the even numbers will remain as even, and again the GCD will be 2 or more than that, so the answer will be no. From this, we can conclude that like if there are more than one odd number in our array and more than one even number in our array, so that is never possible. Means we cannot ever find any x which satisfies the condition. Like there will always be some numbers which are odd and some numbers which are even. So whatever we add to them, like if I add an odd number to them, then these odd numbers will become even and the GCD will be 2 or more than that. And if I add an even number to them, so that these even numbers will stay as even and the GCD will be 2 or more than that. So like if there is more than one odd number and more than one even number in the array, so the answer is always no. Now, another way to see the same thing is that like what are odd and even numbers? These are basically like when you divide any number by 2, if the module is if the remainder is 1, that is odd number, if the remainder is 0, that is even number. So this perspective would be very important in the later one. Now, coming to our next example, let's say that for now we have gotten that like our array cannot have more than one odd number and more than one even number at the same time. So let's take an example where all the numbers are odd. For example, 3, 5, 7, 9, 11, and 13. So here all the numbers are odd. So if I add, we cannot add any odd number here because if I add any odd number here, all the numbers will become even. So the answer will be no. But if I add any even number here, then this will stay as odd numbers, and there might be a case that we might find a suitable even number, right? But let's check it out. So if I add 2 to them, the numbers are like will be 5, 7, 9, 11, 13, and 15. So you can see that 5 and 15 has have their GCD as 5, and 9 and 15 has the GCD as 3. So the answer is no. Now if I add 4 to them, so I can wait, let me mark 9 and 13 also, that will be important. 9 and 15. 9 and 15. Now let's add 4 to all of them. So it will be like 7, 9, then 11, 13, 15, and 17. So here you can see that these 9 and 15, this is 3, so the answer will be no. Now if I add 6 to them, so it will be 9, 11, 13, 15, 17, and 19. Now here again, this 9 and 15, the GCD will be 3, so the answer is again no. And now again, if I add 8 to them, so it will be 11, 13, 15, 17, 19, and 21. So here you can see 15 and 21. So this will be having the CDS 3. So the answer will be no again. So you can see it like whatever we add, like we are getting some pairs. Like you can see now this pair is again repeating. Means the third number and the sixth number, this is again repeating. If you add 10 here, you will see that this pair is repeating. If you add 12 here, you will see that these numbers will again have their GCDs, means the numbers at this position when you add 12 or when you add 18, these numbers at this position will have their GCDs as 3. Now, can you see any kind of pattern here? You can find that like whenever we divide these numbers by 3 and take their modulo, so what is the result? So let me write here again the number 3, 5, 7, 9, 11, 13. So if I take modulo 3, so it will be 0, it will be 2, 1, 0, 2, 1. So you can see that like 3 and 9 are having modulo 0, then 5 and 11 are having modulo 2, 7 and 13 are having modulo 1. So whenever we are adding any multiples of 3, like 6, 12, 18, so these are having their GCDs as 3 or something like that. Whenever we are adding something that is like 3 plus uh, uh, like what did we do? Yeah, 4. So 4, 10, 10, 16. So that is basically like 3p plus 1. It is in this form. 4, 10, 16. So these numbers always were having their GCDs as 3 or more than that. Now, whenever we are adding anything in the form 3p plus 2, like 8, then not 8, I guess, yeah, 2, 8, then 14, then these numbers were having their GCD as 3 or like that. So from this you can find the same pattern just like 2. For 2, what we are having, like there are numbers, like let's say these are the numbers 3, 5, 7, 9, like that, and these are the numbers 2, 4, 6, 8. So these are having the remainder is 1, these are having the remainder is 0. So whenever we are adding anything odd here, that is of the form 2p plus 1, so these are having the GCDs as 2 or like that. And whenever we are adding anything of the form 2p, that is even number, so here these numbers are having their GCD as 2 or more than that. Similarly here, like if I group them like this, like here the module is 0, here the module is 2, here the module is 1. So if I group them, whatever we add, we will be having at least one pair which will be having their GCD as 3 or anything like that. Means our answer will be no. So from this we can conclude that like just like 2, we can also divide by 3 and check like if all the pairs, means if there exist two numbers or more than two numbers with remainder 0, if there exist two or more numbers with remainder 2, if there exist two or more numbers with remainder 1. If all the conditions satisfies, then our answer will be no, of course. Like we cannot add any number. Whatever we add, at least one pair will be there, which will be violating the condition, which will be having their GCD as 2 or more than that. So from this we can conclude this. But Now let's take a look like take our next example. So let's make our example from the previous one. Okay. So the previous one was 3, 9, 5, 11, 7, 13. Now what if I erase 9? So one pair is missing. One pair is missing. So here the remainders are like 0, 2, 2, 1, 1. So here there is no one which is pairing with remainder 0. Now can the answer be yes in this case? Let's check. I cannot add 3 here, of course. A big or any odd number, that is not possible because adding an odd number will result in even numbers which will have GCD as 2 or like that. Now can I add 2 here? If I add 2 here, then these numbers will make their pair, means will have GCD as 3, so that is not possible. Can I add 4 here? Then this number will be having their GCD as 3 again, that is not possible. Can I add 6 here? Earlier while I was adding 6, then this pair was making the problem, like there was 9 here, so it was making a problem. But now there is no 9. So can I add 6 here? Let's check. If I add 6, the answers means the summation values are 9, then here it is 11, 17, then 13, 19. Now if you see like this pair, these are having this days on, this pair, these are having this days on. Now if you want to generalize it, so we know that like GCD of A comma B is equal to GCD of B comma A modulo B. This is a general GCD. Now here if I take let's say for 11 and 17, now we can write it as GCD of 11 comma 6 also, because 17 modulo 11 is 6, so 6 and the smaller one comes here, so 11 comma 6. Now from here you can observe that like one number will be that one, that is the difference of these two numbers. Now difference of these two numbers is of course equal to difference of these two numbers, because whenever we add something it doesn't change. So this C, that is the difference of these two numbers. And what is the other number? The other number is something like one of the original numbers. Let's say one of the original numbers is 5 here. 5 plus it was like some multiple of 3. So 3p. It was like that. Now you can see that like the difference was a multiple of 3 here, but the other number, this is not a multiple of 3, because the original number here 5, it was not a multiple of 3, so their GCD would always be 1. This might sound a bit confusing, you can try it yourself only. Here you can see that like their difference, the numbers 5 and 11, their difference is always a multiple of 3, right? Because they are having the same remainders. But since the original number was not a multiple of 3, that 5 is not a multiple of 3, so their GCD will of course be 1. This is for this pair. Now if I take another pair, let's say if I take 9 and 11 here, 9 and 11, so I can write the GCD as like 9 comma 2. Here 2 is the difference between the original numbers like 3 and 5. 2 is the difference between the original number 3 and 5. Now the difference between the original number was not a multiple of 3. That was not a multiple of 3 because the remainders are different. But this number, this number 3, this was a multiple of 3. So after that also, so you can see that like since this is of this one, like one is not a multiple of 3, another is a multiple of 3, so their GCDs can never be 1 here for this example. Their GCD can never be more than 1 in this example. So we can for sure say that like here the answer seems to be correct, means we are getting a proper result, no pair will validate our case. So you might now argue that like this is for this example only, like there might be an example where still we might find pairs which will violate our case after adding this also. So of course we'll check for them. So here I am just checking for 3. So I am just arguing with 3 and multiples of 3. But this is not the end. If we say that it is satisfying for 3, then we'll check for the larger prime numbers. Just like while it was satisfying, this was satisfying for 2, right? Like all these were odd numbers, so this was satisfying. Still we checked for 3 and we found that this is violating. So similarly, since this is satisfying for 3, we'll check for the larger ones, larger prime numbers, and keep on checking until we find a violating case. Or like we'll see that like in nothing violates at all. Now, till when will we check? We'll check for n by 2 numbers only, means up to n by 2. Now, why n by 2? The reason is because let's say there are 10 numbers in the array, n equal to 10. Now, I'll check only till prime number 5. If I have to check for 7, now whenever I check for 7, what are the possible remainders? 0, 1, 2, 3, 4, 5, 6, 7. Not 7, 7 won't come. So here you can see that like is it possible that all these seven all these 7 numbers will have like two num two numbers with this remainder? Like, can I have two numbers with remainder 0? Can I have two numbers with remainder 1? Can I have two numbers with remainder 2? Can I have two numbers with remainder 3? Can I have two numbers with remainder 4? Up to this it is possible. But already got 10 numbers. So can I have another two numbers with remainder 5? No, that is not possible. So in that case, using this part, we can add something that such that like here in this case we can add 2 here, so that this 5 plus 2 becomes 7, and all this like violates the condition. So like we can add something like that, so that again the pairs satisfy our case. That is the thing. Here this might sound a bit confusing, so let's check it again with the smaller one. I'll just like show it shortly. Okay. So the original numbers were like 3, then 9. I'm writing in pairs, then 5, 11, then 7, 13. Now the last for the last example I erased 9. Now this time let me erase 11. So here the remainders are coming as 0, 0, 1, then 2, not 1, it is 2, then this is 1, this is 1, and this is 1. So here you can see that like for 0 we got two numbers, for 1 we got two numbers, but for 2 we didn't get another pair. So here if we add 1 to all of them, sorry, we can't add any odd number, my mistake. So if I add 4 to all of them, like this is after 1, 3 plus 1. If I add 1 to all of them, then this becomes like if I add 4, so adding 4 will give me 7, 11, then 9, then 11, 17. So here you can see that like these would have made a pair if there was some numbers with remainder 2, but since there is no number with remainder 2, so this is not making a pair, and you can see that like there is no other, it is not 11, it is 13. My god. So there are no other pairs that are having this case 2 or more than that. So that is the thing, like while it was 5 here, so I could have added 2 here because I know that there is no pair here, like there is not even a single number existing here. Even if a single number have existed, that is not an issue because I have not, there is not another second number which would have made a pair with it while I have added 2. So here I can add 2 to this, so 5 plus 2 will be 7, and so like the pair wouldn't have existed, and so we might have got a suitable result. So that is the thing, like now here I was showing that like while n is equal to 10, we need to check only till up to 5, that is n by 2. We do not have to check beyond that. This is by pigeonhole principle because we'll always find something vacant here, like there will be always some remainders for which we don't have any numbers, and we'll use that. So we basically need to check for n by 2. So this basically concludes the explanation. I will check the code. So firstly, you can ignore this, like I wrote it while checking for odd and even, but that is not necessary now. So initially I've taken the input and I have inserted them in set. So this is basically checking like whether there is any duplicate or not. If there is no duplicate, so the set size will be equal to n, and so we'll further proceed. If this is not, that means there is a duplicate, and so we'll simply print no and continue from here. Now, as I said, we should only check the prime numbers, and that is also till n by 2. But during the contest, I could not prove that thing much. So what I did is like I checked for all the numbers from 2 to 50 because the range for n is 100, which is quite small. So I checked for 2 to 50. You can check only the till the prime numbers till n by 2. So here I checked like made a map for finding the remainders. So here I have just found the remainders here, and then check like whether there is any means if the map size is not equal to I, that is if there are not enough remainders, just like whenever we check for, suppose if n equal to 10 and I'm checking for 7, so there won't be enough remainders. Or let's say if the numbers are such that the numbers are like 3, 9, then 15. So while dividing by 3, I will get all the remainders as 0, and so like there won't be any number with remainders 1 or 2. So I could add 2 to all of the numbers or 4 to all of the numbers, and that basically will satisfy our condition. So here I just check if the map size is not equal to I, so we can just continue. That is, this is not violating our case. Then again, I have checked like if there is at least one number that is less than 2, that means like this again satisfies our condition. So we can skip from here. If all the numbers are equal to 2 or more than that, then here I made the flag false, and if means the flag will be true, and so if the flag is true, then our uh, condition is basically validated, and so we have made POS, that is possible, is equal to false. The implementation depends on you, can implement it in any way as you like, but basically the concept will be same. So you can also find the exact x using some Chinese remedial theorem, but that will be pretty much complex. So I have just showed you like how to think like that. I hope the idea was pretty much clear to you. Now, if you have any doubt or any confusion, you can ask in the comment section. That is all for this video. Thank you.